let's see here. So how do we create an MO diagram? So you don't have to worry too much about drawing these in this class. For those of you that go on to take organic chemistry, as well as inorganic chemistry, you will definitely get heavy into these MO diagrams, okay? But we start, so I'll go through, the simple molecules H2, and we start by drawing two lines here that represent each hydrogen atom, okay? And then we connect them with this little hexagon type shape, okay? Where this line right here represents my sigma antibond. And if I've got one electron here and one electron here in the atomic orbitals, we, just like when we're doing the Aufbau principle, we put them in the orbital, we populate them by spin correlating, so one goes spin up, one goes spin down, and once we've put two electrons in an orbital, we have to go up to the next successive orbital, okay? So for example, H2 minus, right? So if we compare those two, we know H2 only has two electrons, and that makes a beautiful sigma bond, okay? But H2 minus has three electrons, and so we've got to populate all three of those in this diagram. And so here they are, 1, 2, 3. So you can see now we've got two electrons in a bonding orbital and one electron in an anti-bonding orbital. And furthermore, if we look at He2, right, like bonding to helium noble gases, okay, that would have 4 electrons, right, 2 from each helium, as you can see, here and here. And so we bring them down and populate our bonding orbital. So there's 1, 2 of them. But now we've got 2 more to populate, and there's 1, 2. Okay? And so you can see this question right here, does He2 even exist as a real molecule? So I'll kind of pause for a moment and let you think about that and notice this equation here. Okay, so if you said no, then you are correct. Okay, why? Well, we have this thing called bond order. Don't think too heavily about that. That just means, is it a single bond? Is it a double bond? Is it a triple bond? Etc. Okay. So we can calculate that from this MO diagram. And so that equation goes as the number of bonding electrons minus the number of antibonding electrons, all divided by 2. Okay. So if we look at this H2 right here, we've got 2 bonding electrons. There they are. So we're not talking about the AOs, the atomic orbital electrons. We're talking about the ones that formed the MOs, the molecular orbitals. Okay. So that would be 2 minus 0 divided by 2 equals 1. And that's exactly right. We would predict from our Lewis structure that H2 just has a single bond. Okay. So what about H2 minus? Okay. Well, this would go 2 minus 1 divided by 2, and that equals 1/2. So what is a 1/2 bond? Well, perhaps it's like maybe something like that. Okay? It's an extraordinarily weak bond. And what that means is H2 minus does not readily exist. It can exist, although it would be pretty rare and very unstable. So what about helium, bonded to another helium? Okay. Well, as you can see right now, right, that would go as 2 minus 2 divided by 2, and that equals 0. So nope, cannot exist. And if you think about it, if we were to repeat this exercise for all of our other noble gases, so if we build up these MO diagrams to go up the ladder, right, from 1s to 2s, to 2p, to 3s, and so on and so forth, okay? Then we would see that none of the noble gases can exist as diatoms because of what we see in these MO diagrams. So if we try to bond 2 noble gases together, whether it's helium or neon or argon, etc., They will have the same number of bonding electrons as antibonding electrons, and so they don't form a bond. Okay, so this is why we often call them perfect atoms, because they are happy just as they are. And the last thing I'll say on the slide, what you notice here is there's a mutual benefit for each hydrogen atom to share electrons and bond, and that benefit is the energy is lowered. Look at that. See on this energy scale, okay, the MO bonding orbital is predicted to have much lower energy than the atomic orbital. So that's why things bond. They don't do it just because. They do it because it minimizes their energy. All right. Okay.